Hello everyone. So in this video we are going to understand about the cyclotron. So basically cyclotron is very important in nuclear physics and in radiation physics. So basically cyclotron in cyclotron what we have uh, accelerate we accelerate charged particles. So these charged particles may include alpha particle, beta particle, or protons, or whatever the charged particles. But basic necessity or basic necessary condition is that the particle must be charged. Then whatever the applications you're going to use with those faster moving charged particles, that depends upon, just like in the radiation physics we actually target these charged particles to some tungsten filament where from the X-ray radiations gets liberated or produced, or simply we can also use these charged particles just like the beta particles, like some electrons or positrons. We can accelerate them to a very high velocity. Then those can be used to treat directly the tumor, or simply like in case of the LINAC we use it. Okay. In LINAC we use directly the charged particles like the electrons. So what I mean is that when you accelerate the charged particles, that depends upon whatever the applications you want to have from it. So let's understand the basic principle of it. So if we define here, so first, what is a cyclotron? It's a cyclic particle accelerator. Used to accelerate charged particles, as I said, like protons, deuterons, alpha particle, blah blah blah, but very important, to high energies. And what are you using? We're using constant magnetic field in cyclotron. Okay, we're using constant magnetic field and alternating electric field. We'll try to understand the whole physics behind it, and it's a very easy topic, not a big deal. So basically what we have a magnetic field. We have some circular cylinder here. This is some circular cylinder which has been cut in two pieces, and one is called the D, this is called D, and that is also called the D. And this D is placed in some magnetic field. Let's say some magnetic field, some north pole is here and south pole is here. So magnetic field will pass through this D. So this magnetic field would be constant. And then what we do in cyclotron, we release the charged particle here at the center of this cyclotron. And if you know from the very high level physics, or some graduation physics, or maybe before that, if we send charged particle in magnetic field which is perpendicular, but magnetic field should be perpendicular to motion of charged particle, then the particle would cover circle. This is the very high grade physics. Okay, so if there is some magnetic field going inside this plane, and we are releasing some charged particle in the magnetic field. Okay, in the magnetic field, this is the charged particles, let's say electron, then this will traverse circular path. Okay, this is very basic physics. This is the actually principle of this cyclotron. The principle of this cyclotron is that a charged particle moving perpendicular to magnetic field, charged particle moving perpendicular to magnetic field follows circular path. Okay, and we also know that magnetic field would not be enough to accelerate the particle. So basically it can only change the direction of the charged particle, not the it won't change its speed, magnitude of the speed or the magnitude of the velocity. It can only change the direction of the charged particle. So what this magnetic field does, this magnetic field bends the particle. It bends the particle. And there is also electric field. We hear, actually this is the AC input, okay, high voltage AC signal, and this is attached to these Ds, and they create the electric field in between. Okay, they create the electric field in between these Ds. Okay, the input signal, or the voltage is AC, and that's why the electric field will change the direction alternatively. Okay, I hope you guys know about the ACs. And so this, what this electric field does, and while electric field accelerates the charged particle. I hope you understand the basic principle. So when we release the charged particle in the magnetic field, what it does, it travels the circular path. That means the charged particle will go in a circle, but obviously in the circle the magnetic field would not accelerate it. It will not increase its velocity, the magnitude of the velocity rather. So it will not gain the kinetic energy more and more and more and more. So it won't gain the velocity more and more. So what part does that? The electric field would do the job. Electric field would increase the kinetic energy, or electric field would accelerate the charged particle in this cyclotron. So this is the basic principle, and this is the basic physics. Now let's do a simple mathematics, so that we would be able to cover certain things. So now we know this charged particle will go in circular motion in the magnetic field. If there is some circular motion, there must be some centripetal force. And in a magnetic field, this magnetic force equals Q V cross B would provide the centripetal force. So since V and B, let's say this is the velocity direction and B is inside, that means they are perpendicular, and this is the basic condition as well. The magnetic field and the velocity should be perpendicular to each other. So this is VB sine 90, which is 1. So it will be QVB equals mv square by r. Okay, so this is actually the centripetal force thing. So magnetic force will provide the centripetal force. We can cancel certain things, this and this. We would be able to calculate r, the radius. So that would be mv divided by qb. This would be the radius of the circle. Okay, and we can also find the velocity from here. We can write qbr divided by m. This is the velocity expression. Now this is very important. Why this is very important? Because finally you will understand the limitation of the cyclotron from this equation. Okay, now we can also find the time period. It covers, let us say, this whole circle in 2 pi r. That would be the distance, and its velocity is v. Okay, so we know velocity is total distance, or the total distance traveled, 2 pi r divided by time. So we can find the time period, that is 2 pi r divided by v. Now we can substitute t equals 2 pi r divided by, in place of v, let's put this qbr into m. r will go, so we can find the time period. Time period will be equal to 2 pi m divided by qb. Now this is the time period. We can also find the frequency. Frequency would be inverse of the time period. That would be qb divided by 2 pi m. This is a very basic thing. Okay, now I will explain a very important thing here. See, when initially it covers one, let's say it comes here from here to here, and electric field, that time the potential is adjusted in such a way the electric field would be in this direction between the two Ds, so that it can accelerate the charged particle. Okay, and when it will come, let's say here, okay, the electric field would be in this direction, in the opposite direction. That is the main purpose of providing the the alternating potential, or applied the potential is AC potential. Basically we want coincidence, or there should be harmony. Okay, there should be synchronization. Then particle will reach here, the electric field should be in this direction so that it can accelerate. When particle will reach here, the electric field should be in this direction so that it can accelerate. And finally when it will come here, electric field should be in this direction. When it will go here, electric field should be in the direction, and we can like accelerate as much as possible. Okay, let's say this is some window where from we get it. Okay, so this is the basic principle, and this is the basic explanation of this magnetic field. What magnetic field does, that only can help charged particle to move in a circle, and that won't be able to accelerate it or change its speed. That part is done by the electric field. But obviously if electric field has only one direction, that wouldn't be enough. So electric field should turn its direction or reverse its direction with the particle when particle needs that. So that would be provided by the AC signal or the AC alternating voltage. Okay, so this is the basic principle, and this is the basic physics, this is the basic mathematics, and some basic results of this thing. Now what we do, we do one thing. There is the term called as the resonance in cyclotron. There is a called the resonance. Even though I explained it, resonance in cyclotron. So resonance in cyclotron means that oscillator frequency, the applied frequency, is adjusted equal to the cyclotron frequency. Cyclotron frequency means the frequency of the charged particle, okay, in the cyclotron, and the outer outer oscillator frequency should be adjusted so that every time the particle crosses the gap, okay, the electric field accelerates correctly. If it goes against the charged particle motion, then it won't be able to accelerate the charged particle. Okay, so I'm assuming here some positive charged particle. Okay, I'm assuming some positive charged particle. So now one more thing is the limitation of the cyclotron. Okay, see, the basic limitation is that the frequency limitation, the frequency is given by QB divided by 2 pi m. We know this. So basically if the electric field changes its velocity, there would come a time when velocity would be very high. Very high. Okay, and we know from the relativistic or Einstein's relativity, when velocity is very high, mass would go up. Okay, and if mass would go up and up, then there would be frequency variation. This frequency wouldn't be then constant. Frequency, it would decrease. Because this m would go up, this frequency would decrease, and finally it would not coincident. It will not be coincident or synchronized with alternating input voltage. Okay, so basically then there would be mismatch. Okay, or we should say the resonance in the cyclotron fails. That is why ordinary cyclotron cannot accelerate particle to extremely high energies. So we say it as a relativistic limitation. I hope you understand the basics of this accelerator called as a cyclotron. Thank you so much.